Maybe you can start. So, welcome to the fifth open seminar in Frontier of Nuclear Physics. This seminar series is organized by the Institute of Modern Physics, the key laboratory of nuclear physics and iron being the application of the university, and the Shanghai Research Center for the Theoretical Nuclear Physics, and SFC. It is also sponsored by the program of the introducing talent of discipline to the university. The Journal of Nuclear Science and Technique is live stream on the co-share.com. Today, so it's a pleasure to invite Professor Dieter Hoffmann to give a talk. What are the chances for the p boron alpha to alpha reaction in the race for the fusion energy. And Professor Hoffmann graduated in physics from the Ruhr University in Germany in 1975. And then he completed his doctorate at the Technical University of the Darmstadt until 1979. In 1998, he became a professor of nuclear physics in Darmstadt. In 2017, he accepted a professorship as a special appointed professor under the Thousand Talent Program of China in Xi'An Jiaotong University. Professor Hoffmann is author and co-author of more than 400 peer-reviewed scientific articles. They cover the area of the nuclear physics, plasma physics, and actual particle physics. So now let's welcome the Professor Hoffmann.
Dear colleagues, thank you for the kind introduction and the invitation to speak here today. What I'm talking about is, of course, a collaborative work of many people and many institutions, and they are listed here. Among them, the Institute of Modern Physics in Lanzhou, ENN Research Company, Jiaotong University, and many others, and the Laser Fusion Research Center in Mianyang also. Let me come to the topics. I start with a question. What are the chances for the reaction that we call proton-boron fusion in the race for fusion energy? Well, I just want to give an answer. I think proton-boron fusion is the dark horse in the race for fusion energy. I'm not sure if you know what a dark horse in a horse race means. Those who are familiar with horse racing, they call a dark horse that no one is supposed to be significant in the race, and suddenly this turns out to have chances to even win. So usually in a horse race, you name winner one was this, and then also ran. Also is proton-boron fusion, but it may be a comer. That means it comes up and may even have the chance to deliver us fusion energy. Well, I want to take you to these topics, and so I don't read them to you. I start with the introduction, and the introduction is for the benefit of students or also for people who are non-experts in this field. So when you hear a talk of well-known people about fusion, then you always get a couple of terms. It will be zero emission carbon and much more efficient than others, perfect source of energy, And also they say we want to take the fire of the stars down to Earth. This is not exactly a lie, but it is also not exactly true. And so I want to start with this. Let's look at the fusion reactor that is in our neighborhood, and this, the only fusion reactor that we have in the neighborhood that is running is our sun. And there the fusion reactions take place in the very interior of the sun, where the conditions are, as I have listed them here, at temperatures between 15 and 16 million degrees. Let's have a short look. Probably most of you know, but I just want to remind you what the sun is doing. And let me also mention that what the sun is doing, we cannot do on Earth for energy production. So the sun is taking 4 protons and converting them into helium. And this means you have to also to emit two protons, and here are the neutrinos. I forgot them here. And you get an energy of 26.7 MeV. So that means 2 protons have to be changed into neutrons, and this is the weak interaction. And this is one of the reasons why the sun or other stars burn so long, because weak interaction, as the name says, is not very strong. And this takes too long on Earth. So on Earth, we have to do something different. And that means exactly what the stars are doing in the first phase, namely burning 4 protons into helium. This we cannot do. Let's just ask the question, how long will the sun do it? We know how much energy the sun is radiating. We use the solar constant that is 1.4 kilowatt per square meter at the outer atmosphere. So that means in total, the sun radiates more than 10 to the 26 watts. And with the equation I showed just before, that means the sun is burning 10 to 38 protons per second. A huge number. However, the sun consists of approximately 10 to the 57 protons. And so if you divide these numbers, you come up by 3.3 to the 18 seconds. And everybody of you probably knows that a year has pi times 10 to the 7 seconds. So if you put this in, you come up to 10 to the 11 years. However, this assumes that all of the sun's hydrogen is burning, and this is not true. This process occurs only in the center. So the lifetime of the sun will be approximately 10 billion years. But this is long enough, and we know that the sun is halfway through their lifetime. So that means if we want to use nuclear energy for producing energy, that means in principle we have to harvest nuclear binding energy. And also this graph is probably well known. It shows the average binding energy on the left as a function of the mass number, binding energy per nucleon. So you see it starts with deuterium. This is at 1.1. Nuclear physicists probably remember the binding energy of deuterium is 2.2 MeV. So dividing it by 2, you end up at 1.1. And this is the fusion processes. You have helium here, and well, at about mass number of 60, there is the maximum, and then it decreases. Here we have uranium. That means on the right side of this graph, you do fission to harvest nuclear binding energy, and on the left side of the maximum, you do fusion. And well, this is all due to the mass defect, and this is also very well known that 4 nuclei, 2 protons, 2 neutrons, have a little bit more mass than the helium nucleus, or the mass difference is on the order of 10 to the minus 25 kilogram, and using Einstein's formula, energy is mass multiplied with the square of the speed of light, you get the energy, and this is quite a lot. So, as I said, the real fire of the star we cannot do on Earth. We have to operate with the right charges. And the most prominent among the fusion reactions that are studied for energy production is the deuterium-tritium, shown here. So if you take deuterium plus tritium, you produce a neutron, a helium and a neutron, and you get approximately 17.6 MeV energy. You need a ignition temperature here. It's said of 40 keV, 40 million degrees, so 4 keV. Of course, there are many nuclear reactions that have a positive Q value. For instance, here I have listed deuterium plus helium-3 and deuterium. Well, deuterium, helium-3, there is not really not much helium-3 available at the moment. Maybe we find more helium-3 on the surface of the moon deposited by the solar wind. So these are all nuclear reactions that you can consider. And I have not listed the proton-boron reaction here. I will come to this a little bit later. Let me, or allow me, to make a couple of remarks on fusion, which at the moment is DT fusion. Well, there were in 2021, so not long ago, a number of remarkable progress in fusion. Here I have the picture of the Hefei superconducting tokamak. They reported 100 million degree plasma confined for more than 100 seconds, and even 160 million degree. So this is a big step forward here in China. Let me put a grain of salt into this. This is a hydrogen plasma. This is not a fusion experiment. Usually you say, now we take DT and then everything will work. This has to be shown. And at JET, they showed 59 megajoules of fusion energy, actually in a DT experiment. Usually in such devices, DT experiments are the end, because then you have contaminated your device with radioactive tritium. So they do these kind of experiments only in the end. Well, this is now from the beginning of this year, BBC, breakthrough in nuclear fusion. And since we are in China, this is what I read daily, the China Daily, and even there, nuclear fusion is mentioned. Nuclear fusion dreams moves closer to reality. Somewhere I have the date. This is 2023, 11th of January. So not too long ago. And they all report about an experiment that was done at the Livermore laboratory. There they, and since this was such a success, and I come to it, a large number of private enterprises popped up to promise to do fusion, to build a reactor within a time frame, they usually say 20 to 40 years. I'm afraid they overpromise again. And I will say something to it. There was a meeting in the White House on fusion, and most of these, let me with the laser pointer here. Most of these companies were present, and I'm just look for focused energy. Focused energy is very interesting for me because one of the co-founders is a student of mine, and he is now my successor on the chair in Darmstadt. And not because he is my friend and my former student. I think they have a very good program, and they are based in Darmstadt and in Austin in Texas. And they get private money, and the Federal Republic of Germany has promised to help, and also the United States. And he works also at GSI. Some of you know GSI in Darmstadt. When I was head of the plasma physics department, the ministry in Berlin told me, you don't do plasma, you don't do fusion, otherwise, and they would cut me off funding. Now, of course, the same people from the same party, Green, I just say, come to him and say, please collaborate with GSI and help them in the process of fusion. So things change, and now to my remark. The Livermore produced approximately 3 megajoule of fusion energy, and the input, they say, was 2.1 megajoule. So they have 198 laser beams in green light, I think, 500 and some nanometers, that goes into a hole round, a cylindrical hole round. 2 megajoules are deposited there, and they get out 3 megajoules. So this is the first time that there is some gain. However, this is not a lie, but also not the whole truth, because in order to produce 2 megajoules of laser energy in this at this wavelength, they start with 300 to 400 megajoules energy stored in capacitor banks that finally produce the laser beam. So that means that there is still a long way to go, but nevertheless, this experiment is a great success and gives us hope that fusion will finally work. I want to make some more remarks on fusion, and recently I get a lot of heat for these remarks, but I make them anyway. The point is, all these companies that I showed you are still doing, let me say, physics experiment. But in my view, in my mind, a much larger program is necessary. And I will tell you why. The first thing is tritium. Tritium has a half-life of approximately 12 years, so that means it's not around. You cannot get it from somewhere. You have to produce it. And from what I heard, if the ITER in 2030 something will be started, it needs the whole available amount of tritium worldwide to start. So that means right from the beginning, you have to look for tritium sources. Of course, you can make the equation lithium plus neutrons that you get from the DT fusion will produce tritium and something. But this has to be made on an industrial scale, not in a simple nuclear physics experiment that we can do anyway on any accelerator. So this is a technological problem that probably can be solved, but it takes time to do this. So the other thing is in the DT fusion, for my mind, unfortunately, most of the energy, 14.1 MeV, is in the neutron. So the neutron has to go into a wall, and by scattering, and so heat the wall, and then you take the heat and make steam and make a turbine. So this is an inherently not very efficient process. And to make this as efficient as possible, it also takes an industrial program. Next thing, magnetic confinement as the Hefei superconducting machine. I always ask the question to these kind of experts, how long will a superconducting material stay superconducting in this high neutron flux? Over coffee, I told you that I was associated with an experiment looking for dark matter at CERN, and we used one of the superconducting magnets there. We operated for 20 years, and every year we had a quench for some unknown reason. We did not have a high neutron flux. But I'm not a material scientist, but when I see this complicated pictures of superconducting material, I have my doubts that this lasts very long in such a high neutron flux. Okay, let's go to the lasers. The laser needs a final focusing system, and the final focusing, since light progresses straight in a straight line, has to look at the target and the high neutron flux, and this is at the moment very costly equipment. So how long will it last? These are questions that have to be answered. And I'm sure for all these questions I raise, you find a technological answer. However, will this be within this 20, 30, 40-year time frame? And will then the reactor be economical? Because we have solar, we have wind, we have nuclear fission, we have fossil fuels, and fusion has to compete to be competitive on this market. And I have my doubts that this will be achieved in the short time frame these companies promise to their investor. But this is not my problem. Again, I'm sure this can be solved, but will it be economically in 40 years? So at the moment, I think we still have to do a lot of basic physics, better knowledge of laser plasma interaction. And since you are dealing with temperatures in the regime of 300 electron volt, it's a radiation dominated regime, and you probably have to do it fully relativistic, which until now is not yet done. Probably you have to go from indirect drive to direct drive and so-called fast ignition, and all this has to be shown, and I think this takes time. Now let me come to the proton boron. Well, and I say proton boron alpha to alpha reaction. I sometimes hesitate to call it fusion, because in the end you have 3 alpha particles, and proton plus boron and divided by 2 is more heavy than the alpha particle. Well, but this is semantic. Let's call it fusion or a nuclear reaction with a positive Q value. So some details of this. So in a nutshell, always this kind of picture is shown. So you have proton, you have boron, and you combine it to an excited state of carbon, and then it decays with the alpha particles. And in total, there will be an energy release of 8.7 MeV, all in charged particles. Well, we are among nuclear physicists, and what comes out depends on where in this regime of carbon you enter. if you are in the regime of the giant dipole resonances, there are a number of decay modes. There are also side reactions that produce neutrons, but on a level of 0.01%. So I tell my colleagues, don't tell the public there is no radioactivity. There is, but on a lower regime than fission or deuterium-tritium reactors. And in total, I think if we get this working, a reactor will be more easy. So I like, first of all, I made this picture myself. So I like to look at this reaction in this way. You have proton and boron. You produce excited state of carbon, and then you end up in an excited state of beryllium with one alpha particle, and then the beryllium decays, and this is a two-particle decay. You have 2.9 MeV, and these two alpha particles down here may share the 2.9 MeV in a statistical way. So this is the main reaction channel. As I said before, there are other reaction channels also, and this is was already presented by Becker et al. 1987. By the way, this experiment was done at the dynamitron tandem machine in Bochum, where I graduated with DTN helium-3 reaction. Okay, so you see, you produce boron plus proton, you end up somewhere here, and this is the most prominent decay, 5.8 coming down here, and then here this alpha decay. So in total 8.7 MeV. That means if you look for a spectrum, and again, this depends on the proton energy you have, but we are speaking of an alpha 0, where it goes directly to the ground state of beryllium. Then this alpha 1, this has 5.8 MeV, and then this continuum where the energy is shared. So now, to make you more attentive, I want to tell you a story. How did I come to proton boron? This was 2018 on a conference in Kanazawa in Japan. I had a talk on high energy density physics induced by intense heavy ion beams. And on the conference dinner, I was sitting next to a scientist, and we came into talking, and he asked me, what do you think of proton boron fusion reaction for fusion energy? And guess what my answer is? I said, forget it. Doesn't work. And so we were talking a lot, and he said, well, anyway, wouldn't you like to come to us and give us your opinion why this does not work? And this was the ENN research company in Lanfang. And as far as I know, they make their main money from selling natural gas to 100 million customers. But why do I and many of my colleagues even today say proton-boron fusion does not work? It's very simple. Look at this graph. This is the cross-section as a function of center of mass energy for a number of reactions that I mentioned before. Here you see the DT reaction. This has a cross-section of approximately 10 barn. We nuclear physicists like to speak in barns instead of square meters. And this maximum of the cross-section is at about 60 keV. Now look at proton boron. Well, it comes above 1 barn at 600 keV. All of us know from undergraduate physics the Stefan-Boltzmann law, power is sigma times T to the 4. Well, going a factor of 100 to the 4 means a lot of radiation. Everybody knows this. If you have an oven and have higher and higher temperature, you have to have more and more fuel. The part of the radiation that is in the X-ray regime will not be redeposited in the plasma. So this is a loss term. So everybody will tell you, first of all, too high energy, and then the radiation losses cannot be overcome. What they don't say in parentheses is in equilibrium. All this is in equilibrium, and that means, well, if you really think about it, you have to do something. In my plasma physics lectures, I let students calculate the Lawson criterion and then make a graph of the fusion power as a function of energy and the Bremsstrahlung loss. And if you do this for dt, you will have the line somewhere here, crossing here. And that means at about 4 keV temperature for dt, the fusion power is higher than the radiation loss. If you do the same calculation for any of the other fusion reactions that I mentioned before, you will have a picture like this. Bremsstrahlungsloss is way above the fusion power from the reaction. And this is why usually I could stop here. However, I still have 30 minutes or 15 minutes. I go on. Well, so you have to reduce Bremsstrahlung. And how can you do it? Usually you have 50% protons, 50% boron. Now you take 10% boron, 90% proton. Of course, you reduce your reaction rate. Well, and then there is a question of the cross section, and this is why some time ago we started at SINAP to measure the cross section. I come to this later. So this is an example I took from one of our previous calculation for the densities are important. And if you have 50, 50, you have 25. And if you have 60, 40, 24. So this is a reduction of 4%, but the reduction in the other for 20%. And we calculated this for a pellet gain. So what I want to say, if you reduce the fraction of boron, the reaction rate reduces, but not at the same amount. So you can come up with a Z effective, it's instead of 9 to something like 2.4. So, and now let me talk about what we did for proton-boron fusion. And here I have to mention a large number of colleagues, and here I just mentioned those from ENN, from IMP, and some from our institute. When we started, I told my colleagues, the first thing is you have to have a good target. We nuclear physicists know this, and since I had no idea about the properties of boron, I said, let's make a boron target. And so I asked it at my home institute, and I found out this is the first difficulty. And so the colleagues at ENN have a plasma vapor deposition facility where they can make excellent targets. So this is a view. This is some of the targets that were produced for experiments at the IMP. where 100 to 300 keV protons are available. So since we had a target, we started to do experiments, and one of the first experiments was at IMP and the other one at SINAP. And you see the date, this was October 2019. So there we did this experiment, and for some reason the cross-section measurements didn't turn out, but we measured something. So this is one of the challenges, because it's not quite clear how what is the real value of the cross-section. And later I will come to laser-produced protons, and they have a broad spectrum. So it would be nice to know the cross-section up to 10 MeV. More is not necessary. So this experiment we did in Lanzhou. This is a logarithmic scale. Here you have the alpha 1, the alpha 0. This experiment took 13 seconds. Then the detector was saturated. And therefore we decided to go to Shanghai, and you see we have this very nice spectrum, alpha 0, alpha 1, and here I do not show the other background from the two-particle decay. So we had really nice spectrum. And then there was the question, oh, I forgot to mention, this was a publication by Heinrich Hohrer, and it was in Laser and Particle Beams. At that time, I was editor-in-chief of this journal. And in many publications and in many simulations, even today, even though I say this on any conference, you see that they thought the 8.7 MeV alpha particles that come out all have the same energy. And from the spectra, I just showed you that no, this is not clear. And so this ended the fairy tale of the three alphas at 2.9 MeV. And even, as I said today, many simulations still does. Now we do some experiments. There were, starting in 2005, experiments where a high-power laser beam was shot onto a beryllium, onto a boron target in different configurations, which we call picture capture or in-target. In-target means you have a boron target, go with a laser and then look for the alpha particles. In a picture catch, you have a laser that produces a strong beam, and this beam then goes onto a target. So these results that you see here raise the hope that one can do something with proton-boron in non-equilibrium. And since this was such a high yield, the next question was, is there an avalanche effect? Which means that the alpha particle that is produced with 5 point some MeV knocks into a proton, and this proton induces another fusion reaction. Well, we looked in detail for this, and this is the result. These assumptions are either mistaken or are not supported by quantitative analysis of several critical important problems of the effect. And I just can underline what my friend Mikhail Shmatov says. There are a couple of publications. So there may be a negligible quantity of protons that have been knocked on, but not an avalanche that produces this. So then we did some experiments at 140 keV. Why 140 keV? Let me just come back. This is in this regime where there is a resonance. This resonance energy was just available at the IMP So we did this experiment, and we had radiochromic film to detect the alpha particles. In principle, this was in preparation for the laser experiment in Mianyang, so that we knew how to deal with radiochromic film. So these are spectra, and well, this is what we measured, and the data are well in line with what has been measured previously, so no surprise. At the same installation, on the left is the Chinese version, on the right, the international version of the same experiment. Again, at Lanzhou, and this time at ENN, they prepared a hydrogen-doped boron target. Let me skip the details of the experiment, so you trust me that we were now able to do experiments. Now the result. We see an increased yield with hydrogen-enriched targets. The point is, I have no explanation for this. And this is the reason why until now we could not publish this. So I was under the naive assumption that we present the experimental results, and they, without doubt, we believe that the results are true. We see more yield with hydrogen-enriched targets. And since, well, I wanted to ask the community, maybe they have ideas. In another experiment that I will show you soon, we think we know why, but not at the conditions with a beam that is measured in nano amps. So you don't create a plasma or large fields with the beam. So at the moment, I simply have no idea to explain this. I just show this. Now we come to the experiment that we did at the Laser Fusion Center in Mianyang, and here are all the people that had to be present with it. Just look at this. This is for the laser people. A picosecond laser with 120 joule, a nanosecond laser with 150 joule, and the target is a foam target enriched with 20% boron. Now, the target is very important, and we did since 2021, we did a number of experiments that had nothing to do with proton boron, but with the same target configuration. The target is a foam, and this has a nano and a microstructure. The diameter of the pores is micro. The thickness of the foam is in nanometers, so a micro nanostructure. Foam density 2 milligram per cc. It's just air with a little bit around 1 millimeter. And this was heated indirectly, like at NIF. So this foam is attached underneath a gold hole round, and the hole round is heated by a nanosecond laser. So we achieve approximately 20 electron volts in the cylinder, and the foam is heated to approximately 17, 18 MeV. In one of the previous experiments, we looked for the radiation of the foam. Interestingly enough, there is a very hot white dwarf that has the same atmosphere, and so we could have a model atmosphere of the hottest white dwarf in our galaxy, and this was then an astrophysical journal paper. But I show you this because I want to tell you that we were doing good spectroscopy on this. And this is the whole realm here, and with a pinhole camera, and this is the X-ray flux as a function of time. And if you fit it with a Planckian curve, so you get the temperature of approximately 20 electron volts. And now all our knowledge that we had on this experiment was used for this experiment. Again, you start with a picosecond laser and you produce a proton beam. Who of you knows about this? It's called the target normal sheath acceleration. It's a very well-known procedure to make very intense protons. Well, we have a shielding that not high energy carbon ions come with the beam, and then this beam goes to the foam target, which is heated, and part of the beam goes without interaction straight through. So we have the proton-boron reaction, since we have doped it with 12% boron and with the radiochromic film, and we now have the necessary expertise. We could measure this, and there's also a Thomson spectrograph. And well, the details of this is really for specialists. I just want to show you the results. And the results are that we, in this experiment, the red is always with plasma, and the cold is where the foam was not heated, just the beam. Even with the non-heated, due to the foam structure and the very intense beam, we have already up to 4 orders of magnitude more alpha yield than you expect from beam-target interaction. 4 orders of magnitude. And when it's heated to a plasma, even more. So if we make a plot, and I have to tell you, the scale is broken here. If we go to down to 0, then you wouldn't see this, and this you wouldn't see. Here you have about 50, but our result is 120. This is just to make the others not to look too bad. This is the result we get, and this is the highest yield normalized to the input laser energy yet. And well, why is it the case? In one of our previous experiments, we found an order of magnitude more stopping. The proton beam is stopped in this foam plasma more than you expect. One of the reasons is this intense proton beam creates an electric field on the order of 10 to the 12 volt per centimeter, high electric fields. And these high electric fields, they accelerate protons in the target. So we do not only have the protons from the beam, but due to the nonlinear conditions that we have suprathermal protons created in the target, and they contribute to the yield. So the foam structure and the very intense beam are essential, and we see a non-linear increase of the yield with intensity. So here I'm at summary and outlook. Give me a minute more. So up to 4 orders of magnitude higher. I think this is a good result. I told you we are working with ENN, and their main project is a spherical tokamak. The project started 2018. The first plasma was achieved 2019, 7 or 8 months later. I saw the bare field. And in Germany, this would take 100 years to do something like this, and in China, some people think the proton-boron reaction is a nice alpha source which can be used for additional tumor therapy. And I also told you that there is a mystery why of the low abundance of boron, lithium, and beryllium. this is something one is interesting also for us nuclear physicists, and we want to investigate this. And this is the final outlook and dream. Fusion, I think it's even more better for space propulsion. I have this picture since long, but I now know that this is a proton-boron machine, spaceflight. Why? Because the passengers sit here and the fusion is here, and if there were many neutrons, they were there already. And if you look into the internet of fusion space propulsion, you see very long spaceships, because way down there is the DT fusion, and up there are the passengers because of the high neutron flux. And proton-boron does not have the high neutron flux, so you can build a spaceship with this. And if you want to publish your results, you are welcome to, this is a Chinese journal with impact factor over 5. Last year it was 6.9. This year it's a little bit lower, and you are welcome to publish there. So I'm stopping.
Thank you for Professor Hoffmann's talk. Now it's the question time. Any questions and comments? Yeah, please.
I have a question too, actually. Why is you say you using accelerator in Lanzhou to accelerate the Jiaotong beam if some hydrogen in the boron hydride target? And we think compared to the pure boron target, the other particle or the movement year is even higher. And so, but you say it's their own question. You don't know why. Rules or see, no, from later.
From the later, I gave a couple of arguments. First of all, this is very intense speed. Yeah, and here we are speaking of 10 to the 16 per cubic centimeter or more. This is nothing you can achieve on an accelerator. Yeah. And so this intense speed creates a field inside the target. Well, in my plasma physics lecture, I always tell the students there is no such thing as an electric field in the target except for the dividends. But in these extreme conditions, it may be over the range of the beam. So we have extreme fields, and then we have these thin layers. Electrons are come out, they pull the protons, and they get in this high field also energy enough to make fusion reaction.
This why.
Yeah, but in the accelerated experiment, we have nanoamps. So this is really one particle by another. So in every many thousand protons go through is out, and then once in a while there is a fusion reaction. So this doesn't change the properties of the target at all. But nevertheless, if we put more hydrogen in, so I have no explanation. So
when the proton hit the hydrogen, so one NHS, one will become two, and hit the boron at the same time.
Yeah, but of course we are part of this also. We have the resonance is at 160 keV. So if you have 200 keV beam and it hits a proton head on, then you have 80.
the cascade, so either problem, and then again problem here.
But with low intensity, how much benefits? It's all these effects happen, but on a scale order of magnitude below this 20%.
The electron with accelerator is the laser, the particle. But according to the ruling, we will also show they say is another mechanism. The stopping power of those beams decrease. It's not with accelerator, but
No, the stopping power increases.
oh.
So
some ways.
Usually you have electronic stopping. So the proton is emitting electrons, and so this is the usual stopping mechanism. And since in a plasma you have free electrons stop much more effective than bound. With this, we have shown an experiment already 30 years ago, but now there is a strong electric field, and this produces another stopping mechanism. And on the other hand, the strong electric field pushes in more protons from the target and creates reaction.
Thank you.
Okay, so any more questions? So online. Let me see. Any questions? Okay. Maybe. Okay, let's make more questions. Thanks, Professor Hoffmann again. Yeah.